everybody listening. So today we want to discuss one of the more complicated mechanisms of aldehyde and ketone reactions involving an oxygen nucleophile. This is called hemiacetal and acetal formation. So here we have the general mechanism of the acetal-hemiacetal formation. As you can see, the starting materials will either be a ketone or an aldehyde, and then one equivalent of an alcohol. There are a couple important things I want you to take note of when looking at this general mechanism. Firstly, the arrows are equilibrium arrows, meaning that the reaction goes in both directions equivalently. So you'll see in our first step, it can either be acid or base catalyzed, and will react with only one equivalent of the alcohol. This produces a hemiacetal. And then, our second step, we need another equivalent of the alcohol, and this can only be acid catalyzed to produce the acetal formation, which has two ester groups compared to the hemiacetal, which has an ester group and an alcohol group. So here, we're going to walk through a step-by-step example. In this example, we are starting with a ketone that is going to go through an acid catalyzed reaction. The carbonyl oxygen will attack the hydrogen to produce an oxonium ion with a positive charge. Formation of this oxonium ion creates a more electrophilic carbonyl carbon. Now in this step, we see our first equivalent of the alcohol, which acts as a nucleophile. So we see the oxygen of that alcohol attack the newly electrophilic carbonyl carbon, which causes the double bond of the carbonyl to be flipped upwards to the oxygen. After nucleophilic attack, we observe an oxonium ion that will need to be deprotonated to become a stable intermediate. To do this, a base will deprotonate the oxonium ion. Now this results in the hemiacetal form. If we were base catalyzing, this is where the reaction would end. But since we are showing you an acid catalyzed reaction, there's more to come. This reaction is acid catalyzed, the oxygen of the alcohol group will be protonated by a hydrogen. This forms a fantastic leaving group. When the leaving group leaves, this produces a highly stabilized carbocation due to resonance. As you can see, we have our second equivalent of the alcohol. The oxygen of this alcohol will attack the carbocation, and if you remember from previous units, this is an example of an SN1 mechanism. This forms yet another oxonium ion with a hydrogen that will need to be deprotonated. So now, as you can see, this is the final step-by-step mechanism of the hemiacetal-acetal formation. Now, I would like to reiterate that this is an example of the acid-catalyzed version, and also, as shown by the equilibrium arrows, this mechanism is completely reversible. So now we are going to show you an example of how we would base catalyze an aldehyde or ketone to form the hemiacetal. So, in the case of base catalyzed, we start with the deprotonation of alcohol. The deprotonation of the alcohol creates a very strong nucleophile to attack the carbonyl carbon, displacing the double bond of the carbonyl. This step produces an oxygen with a negative charge that will need to be protonated. In this step, the oxygen is being protonated to form the hemiacetal. Now that the hemiacetal has formed, the reaction could continue onward to form an acetal, but only if the rest of the reaction is acid catalyzed. However, it is important to point out that since this reaction is base catalyzed, if there is no acid catalyzation occurring after the hemiacetal is formed, the reaction will end with the hemiacetal. To reiterate the mechanism of acetal-hemiacetal formation, we would like to discuss how acetals can be used as protectant groups against reducing agents. In this example, we are going to acid catalyze a ketone to show how the formation of an acetal can protect. Feel free to pause and attempt to do this mechanism on your own. Good luck! So I hope this example really helped you master acetal-hemiacetal formation and learn how to form a cyclic acetal protecting group. Now, I want to run through a couple steps that'll help you nail this mechanism every single time. First, protonate the carbonyl oxygen. 2. Alcohol attacks the carbonyl carbon. 3. Oxygen is deprotonated and the hemiacetal is formed. 4. Oxygen of alcohol group is protonated. 5. H2O leaves. 6. Alcohol, the second equivalent, attacks the carbocation. And 7. Oxygen is deprotonated and the acetal is formed. So these helpful general steps I have are for the acid-catalyzed reaction of acetal-hemiacetal formation. Now, it is important to remember that these are very general steps, and they're really something that you should just tick off in your head as you work through the mechanism. So, guys, this is all I have for you today on acetal and hemiacetal formation. I hope it gets you through your next test. Thank you for listening, and tune in for more helpful hints next time.